Hey, everybody. We're going to finish up some assignments right here. Let me get the real chat on the screen. Office hours, December. Go to the chat. Pop out the chat. Top message. Pop out. Let's do the Canvas content to start. Canvas content. Canvas content is the #1 way to know what the test looks like. So do the Canvas content every day, all day. Here we go. I think MuBot's awake. We'll restart some MuBot. Restarting MuBot here. Crash the world, MuBot. He does that. Oh my god, what's going on in the background right there? You'd have been here for class. Anyways, okay. And MuBot's gonna wake back up. Here we'll put, well, he's gonna be over there now. MuBot, come over here for now. Okay. So Canvas content of the last of the semester. So last Stat 201, last Canvas content. Last Canvas content. Okay, let's do it. And Ignite AI search. Oh, we have that. Did that just get added? Did that just get added? Well, I got new things to look at apparently then. I don't remember that being here just yesterday. Well, we got AI in Canvas now. Well, let's do the Canvas content. Where is it? Canvas content? I don't know how that works. I'll have to check it out. Okay, previewing the Canvas content. Chapter 17, Chapter 19. So once again, you want to know how to solve these. Once you'll see some answers here, but the more important thing is how do we solve this? First question asks about degrees of freedom. Now there's 3 times we've done degrees of freedom in our class, and we were reviewing this during class today, with the 3 times we did degrees of freedom being, magic will go away. We've got the 1 sample t, the 2 sample t, and the chi-squared test of independence are the 3 times we've done degrees of freedom. Chi-squared test of independence is when you have 2 categorical variables, and it's rows minus 1 times columns minus 1. So to solve the degrees of freedom on this, we simply go right here, and we ask, well, what is this? It's a 2 by 5. 2 by 5. So since it's a 2 by 5, you simply reduce by 1 and do 1 times 4. There's also tricks where you can delete 1 row and 1 column. Now, what's important to note here is I'm deleting the totals. You don't use the totals, but I'm deleting, if you were to look at this, like the way I like to make these tables, someone's like, you deleted more than 1. Usually you don't see the totals. A lot of times when I make a contingency table, you just see the values. So that's why it's a 2 by 5. That is often a point of confusion for a lot of people. It's a 2 by 5 because you only count the groups right there. So now when you do the trick of deleting 1 row, you delete 1 row here, and you delete 1 column. This is rows times 1 times columns minus 1. You get the 4 degrees of freedom. So there's 4 right there. 1, 2, 3, 4. And there's how to get it. So, hey, Reptar, good to see you there. Is there 5 degrees of freedom here? No, there's 4. The test of a chi-square test of independence concludes color choice is dependent on gender. Which of the following is true? So when you think about the null here, we always put the word independent between the 2 things. Like the outcome is independent of the category. Now, when we conclude that they are dependent, that means we rejected the null. So the chi-square test of independence has the null that the 2 things are independent. You have to reject the null to conclude that they're dependent, which rejecting the null means p-value less than alpha level, which is usually 0.05 unless otherwise stated. So it means we had evidence for the alternative. So the p-value was lower than the alpha level is the right answer. So the alternative would be that the favorite color is dependent or not independent of gender. And to conclude that, we'd have to reject the null. In the chi-square test of independence, large values of chi-square test statistics indicate cause and effect. Cause and effect are what words in this class, Reptar? We know about cause, right? Cause and effect are words we don't like around here. MuBot's going to get mad. We don't cause things. We don't prove things. We don't accept things around here. Statistics is about evidence. Large chi-squared values, which would be way off the edge of the curve. We go look at the chi-squared curve right here. When you get a big chi-squared value, it leads to a lower p-value, which is stronger evidence. So the bigger the chi-squared value, the stronger the evidence. And we did a full example right here in class where we went through and did a test of is there an association between if someone lives on campus and owns a pet? We had the counts: 30 people on campus, or 30 people own a pet on campus, 20 people own a pet off campus, 50 people on campus do not own a pet, and off campus 0 people. Weird numbers, but we did it. Then we did the expecteds and all these things. We got the chi-squared, which was 25, which means we'd go here to 25 chi-squared, and we'd put in the degrees of freedom 1 because it's a 2 by 2. So 1 times 1, 1 degree of freedom, because on, off campus, own a pet, yes, no. You delete 1 on each, and that leaves 1 times 1, which is 1 degree of freedom. And I don't know why the curves are looking weird like that. That's weird. We could reload the page. But it should be find the p-value, and we had a chi-squared test statistic of 25, and the p-value is basically 0. So a large chi-squared value would indicate strong evidence of an association. It does not indicate a cause and effect. We don't do that in statistics. Here we are, and I think it wants what is the correct, is it null or alternative, or what is the correct null and alternative? So we've got people's political views, and we're asking, is it associated with their test score? As in, is there a difference between the means of test scores of very liberal versus very conservative? And I think we're trying to find, is there a difference? So the null has to have the equal sign. So that eliminates this one. Answer C is eliminated because you can't have the non-equal sign in the null. It has to have the equal sign in the null. And I do want to point this out. Whenever you're writing your null, the way you write the null is the following if you're using statistical notation. First off, you go right here and you write HO. Then you write out the parameter you're testing. Then you put the equal sign, and then you put the hypothesized value. So in this test, we're testing the difference between two means of very liberal minus very conservative. Then we do the equal sign, and we're hypothesizing that is 0. Now, once you do this, you write the alternative simply by changing the sign. So everything stays the same, as you can see with the problem, but the alternative hypothesis just changes the sign right here, mu very liberal minus mu very conservative, and we might say it's not equal to, which is when we're testing if there's a difference. So I think it's saying we're testing if there's a difference. I think it is. What is great hypothesis? I think it's just that there's a difference. I don't see a sidedness. So the answer is A. Watch out. I don't love that it's mixed up, but there's the answer. What is not a good way to check the nearly normal? Which one is it? Hey, good to see you, Kendra, right there. And Peyton. So what's not a good way? We could do chapter 19 quiz. We could do chapter 19 homework and then the quiz. We'll do one version of this, and then we could do the quiz. What is not a good way to check the nearly normal? A, B, C, D, or E? What is not a good way to check the nearly normal? A, B, C, D, or E? What's the worst way? This is a tricky one right here. What's the worst way on here? Is it A, B, C, D, or E? What would be the worst way? It says not a way to check the nearly normal. Which one is it? Which one? Who knows? A, B, C, D, or E? It is E. Good guess, though. It's E. The central limit theorem is basically the large enough n condition. And the central limit theorem, good guess. The central limit theorem applet shows us that if we have a very, that one's hard to draw out as a summary. If you have a very skewed distribution, but you have a very large sample size, then the distributions of means will be nearly normal. But if you don't have a very large sample size, the distribution of means will not be nearly normal. So the central limit theorem is basically large enough n, how the distribution of the mean gets more normal for larger sizes of n. So like if it's very skewed, you need greater than 100. Histogram, you can look to see if it's unimodal symmetric. Normal probability plot is the one that if it follows a linear pattern on the plot, it follows the normal, which is kind of similar to the goodness of fit test, which is a test to see if the normal is a good fit. The answer would be the last one. Degrees of freedom greater than 10 is just a sample size of 11 for a one sample t, which really doesn't equate to the data being normal. It would be like that doesn't tell you enough. Does that make sense? So we got a 10 out of 10. How's that sound, Peyton, right there? Does it make good sense? And they'll do one more version of this. We already did this one. This is false. Chi-squared test, then we know the p-value is lower than alpha because we rejected the null. A contingency table is a component of understanding the chi-squared test of independence. Is this true or false? A contingency table, which is this thing right here, is important for understanding the chi-squared test of independence. That's a mosaic plot. And these are the expected counts. And these are like the marginal. And there's the chi-squared value, and there's the p-value. So true or false, a contingency table is an important component of doing the chi-squared test of independence. Is that true or false? That's a contingency table there. That's a contingency table. So the answer is most definitely what? A contingency table is important for doing the chi-squared test of independence. True. And we did this one already, so we can put the answer. It's A. Watch out, it's mixed up. And which of the following is not a requirement for the two-sample T? Is it A, B, C, or D? Which of these is not a requirement for the two-sample T-test? This is Mr. T being mean. If you got this, yeah, look at that right there, just right off the bat. Yeah, because that's for proportion data, right? So once again, check out the videos we have on this. If you get this question, I'd hope this be an easy one because you go random, 10%. And then the last condition is independent means. The third one is nearly normal. So nearly normal is for quantitative data, success failures for categorical data. Nearly normal is not listed there, but yeah, we'll do one more. We did that one so quick. It's like, a contingency table is a key component. True. The overall chi-squared is found by what? A, B, C, or D. What do you do with the cell chi-squareds to get the overall chi-squared? And we did this today. What do you do with the cell chi-squareds to get the overall chi-squared? Just good practice and memorization to be like, you add them up, you sum them up. Exactly. So it's the adding up of them. A chi-squared tests are used for testing hypothesis of the association between two categorical variables. That's literally the condition count data. True. All else being equal, the further the t statistic falls from 0, either in the positive or negative direction, the more likely it is that the difference between two populations means is statistically significant. True. And you see it down here. This is where we landed with the t statistic of 2.5, and it's pretty far away from the center. If we had been closer to the center, it would have been bigger. And I'm glad we got this one because this one's one of the toughest ones for people, but we've done a lot of these p-value problems. So I want you to try to figure out this p-value problem, and it's a really good one if you get one like it on the test. So if you were to get the less than, the greater than, and the not equal to p-values, you could see the not equal to p-value be something like 0.10. So what would be the less than p-value? It's probably more over here. Here's where your test landed at a z equal to 1.64, no, 1.28. So what would be the less than p-value? Be very careful. Does anyone know the less than p-value? So you landed right here. So you have to think for this one, what is the area to the left of it? How would you get that? Who can solve it? Does anyone know the greater than p-value? That's the easy one. Who's got this? What is the greater than p-value? Well, what we see right here, the does not equals p-value is 0.10. So what relationship did these p-values have right here? They have to add up to what? Because what you're doing with these is you're going above a certain point and below a certain point. They have to add up to 1, right? So we know that about those. What relationship does this p-value down here have with one of these up here? What relationship does it have? So they have to add up to 1. But this one is what down there? That p-value at the bottom is always what? What? And you can kind of see it visually. If you look over here, you can see it visually. Because here, I'll show it. I'll map it out for you on the paper. This is the p-value we have. this is the p-value we're looking for. So this is what we have. This is what we're looking for, because that's above that point. Because this is the reflection of it on both sides, the does not equals. This is just merely doing above this point. So this is the greater than. So the greater than looks like that. What would be the greater than? This is the does not equals to. This is the less than. So how do we get these? Any thoughts? I'll answer it in a moment, but I want to see if people can get it. Because this is one of the ones that just stumps people. And it's like, once you know how to do it a few times, you're like, oh, it's easy. So how would you get the green value? How would you get the greater than test? That's where we landed. That's a z-score equal to 1.645. So the green value is half the yellow. So the yellow is 2 times the smallest. So it's 2 times smallest. So this is 0.05 right here. And then these have to add up to 1. So this is 0.95, because you can just see like this is the 5% remaining off that curve. Does this make sense, Peyton? How's this look? Like you would, this is double of this. So you just take that over to the other side, or this is half of this down here. So you can see the mathematical relationships they all have. So when we think about this, it depends on which one we're looking for here. It says the does not equals test. Well, the does not equals test is double the smallest. So the missing one, we have the less than p-value. So the greater than p-value has to be the other side of it. Nice job, Reptar, everyone. So does everyone get, I'm going to do 1 minus. Which one did I just find? The first, the second, or the third? When I do 1 minus this value, I just found which one? I just found the first, the second, or the third. Because this is the less than, this is the greater than, this is the does not equals. So which one did I just find? Well, the third's there, so. Because this is the less than, this is the greater than, this is the does not equal, like, because it's outside the absolute value of it. So I just found the second one, because these two have to add up to 1. And then I just take this and times by 2. And, oops, that's not it. I times it by itself. 0.0066 times 2. There it is right there. And there's the answer right there. That's the answer. A lot of people get stuck on that one. It's finding p-values. Okay. Let's do the... You want to do the quiz or the homework? I'll take a vote right now. What's up, randomized? So vote in the chat right now. Quiz 17 or quiz 19, homework 19. Well, good deal. I like that. Quiz. Peyton votes quiz. We might be doing the quiz. It's not that many quiz questions. Homework first. I think we might do homework first. Well, we gotta see who wins. I think, do we have enough time? Let me see how many quiz questions there are, because we probably do the homework. A lot of people voting quiz. Hey, how's everyone doing? We got a lot of people watching. Oh man, I am so tired. And this semester just drains us. I wonder why we don't just like finish classes before Thanksgiving and then just have all exams online. Like do that. Like have a testing center or something. I don't know. Education. Education. Assignment manager. I don't know. I don't make those decisions. I don't make the big decisions around here. I make the Stat 1 decisions in part. Okay, let me see. Replace questions. Okay, the homework has 6 questions. Let me hit back. Let me look at the quiz. The quiz has, we could do a lot of the quiz. I don't think it's that long. Replace questions. Quiz has 7 questions too. Let's do the quiz. Okay. Okay, here we go. Now, one thing we run into right now, let me see right here, because if you're doing these all by hand, you're going to have a bad time. So, chi-squared test in Excel. Chi-squared test of independence. Make it, I got to find, well, you know what? We could do it. Let's do it ourselves. Okay. So we are going to do the chi-squared test of independence. Probably get good practice doing this. Doing it in Excel. So we're going to need to download the data right here. Get our data. Let me get a certain war story. I've done this one a ton of times. So a certain war story. And this is at 20. 3. Name a question if you want to do it. Chapter 19. Quiz. A certain war story. These are all very similar, and if you notice the steps right here, they're going to be very, very similar. I keep saying that, but we're going to copy the table first, and let's copy open in Excel, and that's an Excel data sheet. It's opening up. Make sure. Okay, why is it off the screen? Always does that to me. Okay, enable editing. So we actually get some more practice doing this in Excel than we would using Jump because we have to do a bunch of the steps. So we're going to write the formulas to do it. So let's go over here and copy our table a few times like we did in class. Why are we making 3 copies of this table? Why are we making 3 copies of this table? We're making 3 copies of this table. Why? Who can tell me why we're making 3 copies of the table? We need one for what, one for what, and one for what. And you can see the formulas right there. There's the formula for the expected, row total times column total over grand total. And then you find all the expecteds. Then you get the cell chi-squareds, observed minus expected squared over expected. Get all the cell chi-squareds right there. And so we're going to delete out these numbers right here. And I need on the edges my totals. Whoops, I shouldn't have deleted these. I meant to actually delete the ones below it. Hit Control Z if you did that. I want these to be empty. And I need the totals on the first table. So we can go right here and go equals sum. And take the sum of these values. What did I do wrong? Sum of those values. Am I going mad? I tried to sum something. I tried to sum the value of sum. That's why. Okay, copy this, copy that, and then equals sum. Open it up, go through there, close it off, copy down, and we're good. And then this one has to be the sum of everything, which can be one of the column sums right there. That's not what I want to do. Equals sum, open it up, highlight the numbers, close it off. So how are people doing on this? Any questions? We're just finding the sum of the table. Who follows me on this? Are we good? How are we doing? Give me some goods in the chat. Like you got all your sums, all your column and row sums. How are we doing on that? Good. I like that. So now we're going to find out all the expected cell counts. So these are the counts, or the observed. I like to call it the observed. These are the expected. And these are the cell chi-squareds. Cell chi-squareds. I can't even speak. Cell chi-squareds. Good. I'm glad John's doing fabulous. And to get a cell chi, to get an expected first, you need to go row total times column total over grand total. And the best thing you can do if you're doing this by hand is you circle the numbers, and then this would be for this cell right here, that cell, because you notice it points in on it. So we're going to write the formulas now inside of the cell and solve. So notice how I'm going to take the row total times column total over grand total. Why am I multiplying? And what we should be able to do is we should be able to work this formula a little bit. The grand total is not going to move, so you have to put dollar signs before it. When we move to the right, that's good. It'll move to the right. And then we don't want it to move. We don't want this to move. We don't want the blue to move to the right, so we need to lock this on D. And we don't want 5 to move down, so we'll lock that. Does that make sense? We can test this out if we copy this to a new cell, and then we look at the formula. Yep. If you notice, it crosshairs in on that one who follows that. So I've got the dollar signs in the right place to lock it. So we saved ourselves a little bit of time because now we can just copy paste. We can look at each of these formulas to make sure it's the right thing, but we can copy paste the formula here. And if you look, you notice how it crosshairs, like this is the row total, column total over grand total. Click on another one. This is the row total times column total over grand total. Click on another one. This is the row total times column. You could write all of them individually, or you can do what I did. Doing good. Just type a capital Y, or just type a Y in the chat. We have now found all of the expected cell counts by doing row total times column total over grand total. So there's all the expected values, which it might ask us for, and we can just input those in. Good, doing good. Nice. And now we need all the cell chi-squareds. Cell chi-squareds are found by doing observed minus expected squared over expected. We can kind of take the same idea. Let's just rewrite one. So equals right here, and then we do observed, which is here. That's the observed, what you saw. And then we have to do minus expected. And we're going to close this off here because we are going to have to square it. So this is an order of operations that needs to be done there. And then we divide by the expected value right here. And so this is going to, I think actually this will move perfectly around the table. I think it will, because if we move this down, I think it perfectly moves around. There we go. I think it did it. Yeah, if you look, it's doing this observed minus this expected squared over expected. So we just did all the formulas right there. Now, what is our Pearson chi-squared? How do we get the Pearson chi-squared? Good thing you need to know. Another teaching to the test moment. How do you get your Pearson chi-squared? How do you get your Pearson chi-squared? What do you do to get the Pearson chi-squared test statistic? You do what? Which we have it listed right here. Add all the cell chi-squareds. Peyton on fire right there. I like it. We got to throw you 50. We've been saying 50,000 points for office hours. Peyton, get everyone that 50,000 office hours points. You take the sum of all the cell chi-squareds. So we should be able to do that right here, and goes equals and then sum. And there might be a way. There might be a way in find p-value chi-squared function Excel. There might be chi-squared distribution. Oh, equals. So I'm going to write this here. What are the degrees of freedom? Who can tell me the degrees of freedom for this test? We might not even really have to use the applet. What are the degrees of freedom? You have to say, Brian, this is a what by what? Brian, this is a what by what? And Peyton's right, it's 2 degrees of freedom because it's a 3 by 2. So there's 2 degrees of freedom. So the degrees of freedom is 2 because there's 3 rows and 2 columns. Delete 1 on each. 2 times 1 is 2. Now let's get the p-value, and I'm going to see if this works. The p-value is going to be basically 0 as far as I can tell. It's saying it should be equals to chi-squared distribution right-tailed test. That makes sense right there. So click the chi-squared distribution right-tailed test inside of Excel. Enter in your chi-squared value and your degrees of freedom, and you're going to see about 0. It's about 0. It was way off the curve. What is the multiply button in Excel? Just add a star right there. Which one are you wondering about, Steven? Or let me know which one you're stuck on or anything. Let me know which one you're stuck on. But we just did the full test. We did the sum of the cell chi-squareds. Yeah, I think we've done it. Let's go look at this. The null hypothesis is going to be that the two things are independent. The alternative is that they're not independent. Take all your values from your expecteds that we have. I'm going to round them to 2 decimals. This is about as quick as jump. It's about as quick. 2 decimals. Don't make errors. 56.08. Really, I can't tab. Really. 16.92. 32.26. 9.74. Lim is 27. I don't think any go out of order. 27.66, and this one is 8.34. And then the chi-squared test statistic was 58.31. And degrees of freedom was 2. P-value was 0. So do we reject the null or not reject the null? What do we do? Do we reject the null or not reject the null? The p-value is 0. That's about as clear as a thing as we could put on a test. The p-value is 0. You definitely reject the null. We reject the null. There is strong evidence. So you conclude that they are not independent. We should get 100. Yale. Oh, that's a good question. It's a good question. And we can do, a lot of these are basically going to be the same. If you look, this is literally the same question, but what is different about this? What is different about that? Or put a question in the chat that you have, and let's do a question you have. This one's the same one, but what's different about this? Now it's a 3 by 3. So there's 4 degrees of freedom. It's just run a little bit differently. I think this is the one that there are different degrees of freedom. Yep, and then who knows what will happen when we run the test. Does anyone have a... Oh, this is easy. Degrees of freedom on the chi-squared test are the dimensions of the table. Rows and columns determine degrees of freedom. Boop. From all the chi-squareds, the sample size assumption is checked by the expected cell count frequency. We must have at least 5 expected cell counts. Most pregnancies are full term. Let's do that. Here we go. Okay, so we're going to bring this over. Let me put the note in. Sorry, yesterday I forgot to hit save notes. Save! Okay, let's do it. And I'm glad, like, we did an example in class today, but I think this is where you're really going to learn. Like, if you do a few of these, you'll get it, I think. Okay, so we're going to bring this over to Excel. Now, don't even look at what they're saying. Don't look at this nonsense, because don't look at that. Let's copy to Excel right here. And now let's open in Excel. Okay, so now what's the first thing I'm going to have to do to this table? I'm going to have to add the what's to the sides of it. I'm going to have to add the what's to the sides of it. Like, you tell me, or I'll do my copying of it. But I'm going to have to add to the sides of it what? Think about what I did last time in the last one if you're here for that. These are the counts. These are the expecteds. We'll delete it in a moment. These are the cell chi-squareds. What am I going to add to them? Down here. The sums, exactly. So we're going to go equals sum, and then we're going to take this and close that. Take this and do that. Equals sum. Open it up right here. Boop. Boop, boop. And then do this. And then equals. And it doesn't matter which way you sum.
It doesn't matter.
You can sum these up like that. There we go. So now we need to find the expecteds. Do remember, because I know we've already done this, but the expecteds are the row total times column total over grand total. So we have to use this. And you need to know how to do this on the test. That you can get an expected cell count. Like, you can check some of your work. This expected cell count right here would be these values. So we go 13,332 times 64 divided by 1900. And it's going to be about 44. Hey! I should have said 45. Sorry. Okay. My brain's working again. So now we're just going to write all of these inside of here as a formula. And so we take right here and we go equals and row total times column total over grand total. We're going to lock the grand total so we can copy this around. That's not what I wanted to do. We're going to lock the grand total. If you put dollar signs, it locks it in that position for that row or that column. And then we need the red one right there to be locked that it won't go lower than 6 when we move this down. And is that right? Yes. It can go to the right, though. And then this one needs to be locked. It can't go over from D because it's going to stay on D. There we go. Once again, if you're looking at it, here's what to lock on it. You lock D, you lock B, you lock 6, and you lock the full other one. And you'll know you've done this correct if you don't get any sort of errors. I wonder if I can just go here and copy like that. I can. And there's that number we found, confirming we probably haven't done it wrong. Because I found this one manually, and you can also see how they're calculated. Make sure, like when I highlight this, it should have 133 and 84 and 1900. There you go. But I think people kind of get it. Is this making sense? Who feels like this makes more sense when you see this right here? That it's like, oh, this cell right here, row total times column total over grand total, and it achieves this value down here. Like, I hope that's making sense. Let's go to round these to 2 digits. I'm clicking the top value, then holding shift, going to home, and deleting decimals to go to 2 digits. And now let's do the next one, which is the cell chi-squared. Nice, Reptar. And the cell chi-squared, a cell chi-squared is going to be the observed minus the expected quantity squared, which is just a discrepancy squared to make it positive, over the expected, which standardizes it via how many we expected to see. And this one's nice and easy because we can just go here and do observed, which is the same thing as count. Those are synonymous words. This is how many we count in this area. This is how many we observe in this area, the actual value. And then observed minus expected. Let's put it in parentheses. Parentheses, observed minus expected quantity squared divided by expected. And this one just copies all around. So now that we have all the cell chi-squareds, what do we need to do? Now that we have all the cell chi-squareds, what do we need to do? So we just found all the cell chi-squareds. What do we need to do that we found all the cell chi-squareds in this test? What do we do that we found all the cell chi-squareds? Sum them up. Almost like that's on the test sometimes. You sum up all the cell chi-squareds, so we're just going to go down here to the bottom and do the test statistic. also known as the Pearson chi-squared test statistic. So the test statistic is going to equal to, you just take these and sum them up. Boop, boop, boop. And there's the, oh, we didn't get a big one right here. That's smaller. What are the degrees of freedom? You have to say, Brian, this is a what by what? Brian, this is a what by what? What are the degrees of freedom for this test? Which tells us the shape of the chi-squared we're working with. What are the degrees of freedom? You have to say, Brian, this is a 4 by 2, 4 rows, 2 columns. Do not count the totals. And then you simply delete 1. Degrees of freedom are 3. 3 times 1. So degrees of freedom are 3. Yay! 4 by 2, 3 times 1. And then we get the p-value right here. There's a function in Excel, as we can see, to do this. For chi-squared right-tailed test, because we're plotting something more extreme than it. So it's a chi-squared right-tailed test. Double-click it. Enter in your chi-squared value. That's what x is, your value of your chi-squared statistic. And your degrees of freedom are 3. And you can see what happens if we were to have a bigger chi-squared. The p-value is going to get smaller. I'm just showing you this to like show what happens. Bigger chi-squareds lead to smaller p-values. They do not show cause and effect. But that should do it. These should be all the answers. So we know with the chi-squared test of independence that the null hypothesis is that they are independent, and the alternative would be that they're not independent. The chi-squared test statistic we obtained to 3 decimals. I'm going to round it over here. It was just that right-tailed test chi-squared we got. This is the chi-squared, which is the sum of all the cell chi-squareds. So I could just look at it, 2.655. And the p-value is actually larger this time to 3 decimals. It's 0.448. And our p-value is way bigger than alpha. So which one of these makes sense? A, B, C, or D? I can see the answer pretty quickly because there's only 2 things I'm looking for. The p-value is way bigger than alpha. What have I done to my desk? Oh, why are they hitting something? The p-value is way bigger than alpha. Way bigger than alpha. My p-value is way bigger than alpha. I'm going to do what? Is it A, B, C, or D? It's a good one to know. It is D. Yep, because the p-value is way bigger than alpha, greater than the level of significance. There's not evidence to conclude that they are not independent. We should get 100. Yay! Another one? Another one. Well, these are the easy ones. These are the really easy ones. Okay, suppose we do a chi-square test of independence. Which of the following... oh, this one's tricky. I don't like this one. Let it fly. Let the null fly. John got it right there. It says we end up rejecting the null. So then... I think it's we conclude there's an association. I've got this one wrong. There it is. There's that one. A poll investigated. I think it's this one. This is almost it, Peyton. Look at this. We're gonna... Well, might as well just do them all, right? Okay, a poll investigated. People have to search for those other ones. You gotta watch the office hours. Okay, 03. Stat 201. Chapter 19. Quiz. A poll investigated. I want your help as I do this. Let's get this question done. Okay, we're not even going to look at their questions. We're just going to do the chi-square test of independence because we can do this without my Pearson prompting us. So we're going to copy this over into Excel. We're going to open up Excel right there. And here it's on the other screen. And we'll bring it over. First thing we're going to do is we're going to copy this to make a table because these are just the observed right now, oftentimes called the counts also. But we're also going to make a table here for our expected and our cell chi-squareds. These will be the expected value, what we expect if the null is true, and these are the cell chi-squareds. So cell chi-squareds. Let's delete out the values in here, and then we need to add what to this table of the observed. The what's. Just tell me it's a 6-letter word. You know what it starts with. I can give you hints. But we need to add what's to this right here. We need to add what to it. We're getting faster at these, I think. Because I wish they just gave it to us. I don't know why they don't. The margins, the marginal, yep. So do sum right here and add up the values. And then copy over. And then you could do equals sum of the whole table. Doop, doop, doop. And then equals sum of these. This is sum of these rows, and you can copy the formula down. Should just like be like add margins. There we go. There's the marginal totals right there with the total. Now, this is so important because when you do, what am I showing you right here? What formula have I written? This formula of 94 times 76 over this is the formula for what? What did that find right there? Like, if I solve this, I have found how many Republican people from the West I what? So this formula is row total times column total over grand total. What does this find? It's row total times column total over grand total. Expected count. That's how many you would expect via random chance. And I think it's easy if you look at an example like this, because if you don't even look at the totals, can I not draw on this now? If there's 80 people on campus, does this make sense? There's 80 people on campus, and half of the people own pets. How many people do you expect to own pets? Just think about this. I say I have 80 students who live on campus, and I know half of the people on, not half the people on campus, but half of students own pets, and there's 80 students who live on campus because it's half of 50 out of 100. How many students on campus would you expect to own pets? 40. And that might not be what you see. We see that only 30 own pets, but you can do the math right there, and that's when you do 80 times 50 over 100. You're actually doing the rule of independence because you're multiplying two probabilities. Funnily enough, the math, if you're really wondering, the reason it works is you're saying the probability of living on campus, the probability of owning a pet is this, the probability of living on campus is this, so the probability of both occurring is equal to this, and then when you multiply by 100, you get the count of it. So you're actually doing the rule of independence by multiplying to say, if these two things are independent, then we'd expect 40% of people to be on campus owning a pet. And so that's why it's called the expected, because the multiplication rule has the rule of independence. So when you multiply them, you're doing that. And then when you multiply it by 100, you're figuring out not the percent anymore, but given there's 100, 40% of them. So that's why if you put the 100 back over here, the 100 actually cancels. And you cancel this with this. And what do you get? You get row total times column total over grand total. Does that make, I don't know if anyone followed that. Like, that's what you get when you solve it out. You're actually doing the multiplication rule, but multiplying by 100 also. So, yeah, that's why we do this. That's the math behind it all. Someone might have just been like,
wow.
Okay, so we have to go row total times column total over grand total. So this is the row total. This is the column total. This is the grand total. How do I know if my p-value in Excel? Mine says that's 0. Good question, Steven. Steven, thank you for asking. That's 0. That says 0 as 0. Put 0. Be up. 0. Your chi-squared is probably what, like 100 or 200? Sounds to me like you have a really huge chi-squared. So we're going to lock E, and we're going to lock 5, and we're going to lock this. And then we're going to double check here. If you didn't lock the right cells, it's probably going to leave the table. And once again, check your work by clicking one and looking to see if it's right. As in, like, if you click the middle one, it should have row total, column total, or grand total. So we've done it correctly. Now we're going to go here, and the formula down here for the cell chi-squareds is observed minus expected squared over expected. Observed is there, expected. We'll solve it. Is anyone thinking these are way easier? I get so used to these that I'm just like, we got this. I think these are kind of fun. Observed. Oh, I got to put the parentheses on it, right? Equals to observed minus expected quantity squared over expected. There it is. And we copy and we paste, and there it is. Yeah, I know. Once you know how to do them, it's like, psh, got this. And then you go here, and you need to find the Pearson chi-squared test statistic. Pearson chi-squared test statistic. How do I find the Pearson chi-squared test statistic? What do I do? What do I do to get the Pearson chi-squared test statistic? It's nice and easy to get. The Pearson chi-squared test statistic is what? It's the sum of all the cell chi-squareds. You're not going to get that one wrong. Everyone's got that one here. So here, you take all the cell chi-squareds, you sum them up, and there it is. What are the degrees of freedom? Brian, this is a what I want. Who's got degrees of freedom on this? Because I can get it like that. What is the degrees of freedom on this? We're probably not going to reject null. P-value is probably going to be like 0.33 or something. Yep, it's 4. Brian, this is a 3 by 3. And John, great work, John, right there. This is a 3 by 3, so delete 1, 2 times 2. and then go right here and do p-value. You can use the applets for this, but it can be done here by doing chi-squared right-tailed test. So make sure you do chi-squared distribution right-tailed test, and then you will put in your chi-squared value, comma, I said 0.37, I say. The answer is 0.21. I didn't think it'd be that small. I mean, like, I didn't think it'd be like a statistically significant. I knew it was like somewhere not too crazy. Chi-squared with 4 degrees of freedom. Really? I'm gonna draw my pen. Chi-squared 4 degrees of freedom is going to look something like that. That's a chi-squared with 4. So we landed over there-ish. We can see the actual chi-squared and do it the kind of more traditional method of drawing it out. If we go over here to the chi-squared applet from Adam Spanbauer, and here's the chi-squared applet. So you could go in and put a chi-squared of 4. The more degrees of freedom you have, the more normal the chi-squared becomes. That's not degrees of freedom, that's rounding. So you can see it starts to become more normal, and there's a chi-squared with 4 degrees of freedom. And then we want to find the p-value and our chi-squared test statistic. I'll put it over where I previously drew that because it looks very similar. And then our chi-squared test statistic was 5.78. And I should have put more on that tail. I guess it's 21%, so I should have done a little bit. Yeah. What do you think of my drawing? I've done a lot of these problems. I'd say that was my guess of what it would look like. Anyways, just work a lot of problems for 15 years. You'd be like, chi-squared with 4. Chi-squared with 1's really easy to draw. Chi-squared with 1's kind of neat. It's neat. It looks like this. And then once you get to, if you get to chi-squared with a chi-squared with 200 degrees of freedom will look like that, and it'll be centered at 100. The center of the chi-squared distribution is the degrees of freedom. So it's kind of tricks if you've done a whole bunch of them. So you go to chi-squared with 200 degrees of freedom. It's just really zoomed out right there. Oh wait, I thought 200 degrees of freedom. The center. The center is the degrees of freedom. Whoops! I literally said that and I put the wrong number. Don't listen to me. Don't listen to me. The variance is another. You can solve. There's estimates. We're not doing that here. Okay, should we do? I think we only have one more from the quiz, right? Well, we didn't put the answers in. Okay, let's put the answers in. Political parties independent of region, and the alternative would be they're not independent. The chi-squared test statistic we found is 5.78, and the p-value is, there we go, so 5.78. P-value was 0.02161 or something. What was the last digit? It is, it's 2. So it might get mad at me. I got to make sure I do it very carefully. There's probably a little bit of leeway. Do we reject? What do you think? A, B, C, or D? Help Brian out with this last one. A, B, C, or D? You got this. P-value high, just let it fly. Which one reports to, because p-value is way above the alpha level is 0.05. That's the point at which we reject. We are nowhere near that. So p-value high, just let it fly. Fail to reject A. But close. Oh, wait, so we do not reject, and there's not evidence. So we only have evidence for the alternative when we reject the null. So we do fail to reject, and then there's not evidence. Sufficient evidence is for the alternative. So yeah. No, don't worry. It's just practice. So I want to huge thank you. We'll do the last one here, but you'll notice the last one's very similar. But 50,000 points. Thank you everyone who's practicing. Don't worry about getting it wrong. You're like, oh yeah, reject the null. There's not evidence for the alternative. Oh wait. See, I wasn't trying to say it wrong. Reject the null. There is evidence for the alternative. Do not reject the null. There is not evidence for the alternative. You only have evidence for the alternative when you reject the null. I'll even make mistakes every once in a while. It happens. Okay. Literally the last one. What have we done? You're welcome, Peyton. Thank you, Peyton. Ooh, I fall asleep. My wife made homemade granola bars, and they are better than store-bought. I mean, I know that might not seem like a lot, but I mean, like, what is it? Quaker Mills or whoever makes granola bars. But her granola bars, I wish I had a picture of it. I was like, who took this granola bar out of the wrapper and then put it in a bag? And I was like, oh, these are her homemade ones. They look so perfect. And they taste so good. They've got like honey and seeds and chocolate in them. And like, I got to make sure I don't just eat all the granola bars. I don't think she understands me. I don't, thank you. Yeah, John knows. I'll say this and then we're going to do this problem. Zaymon, I think there's something about who is like me? If you open up a bag of potato chips, you got to watch out. Even a family-sized bag is in danger. If you open up a thing of cookies, like I opened up some of those Keebler Elf M&M cookies, and I was like, I ate a row, and I was like, I got to stop. And I was like, one more. It's bad. Holiday season is bad. You open up the Pringles can, you know they got that slogan for a reason. Yeah, Raptor knows what we're talking about. You get a pint of like Ben and Jerry's, and you're like, this is meant to be a single serving, right? 5 servings. I don't think it's 5 servings, but you're like, what is the pint? It's a pint for me. Okay, certain war story. A certain story. This is the last one right here. I think this one has a small error in the way they present it. I will put the actual timestamp. I want people to hear about Brian's eating habits. I mean, I do, but you know. Okay, so let's copy this. Copy the table. No way. You got to finish it at some point. You're just helping out. You're doing the work no one else is willing to do. And you know what? Okay, tell me this. Tell me why. Or don't ask why. Don't ask why. 16 candles down the drain. We're going to get like copyright striked. They didn't put 100. Great job, Raptor. They didn't put the totals in. Come on. Come on. All right, let's make our tables. If you watched a lot of these, we're going to do this a little quickly. Made our tables. We're going to call this the count, which is what we observe. So I want you to know that count and observe mean the same thing. This is the expected. We'll delete out the values and add in expected here in a moment. And these are the cell chi-squareds, which are the observed minus expected squared over expected. They're a metric of deviation from what we would expect. We square it so they're positive, and we divide by the expected to standardize the difference. You might wonder why, I'll just draw this out for anyone listening. I like talking about it. So when you think about this, if you observe, because it's observed minus expected squared quantity over expected. So in one example, you observe a candy bar costs $100, but you expected it to cost $1. We make our math easier. $101. So that's a difference of 100. And with your expected of costing $1, this would be a huge wow factor of a chi-squared of 1,000, because that's 100 squared or 10. My brain's not working. Why is it? It's 100. There we go. 10,000. But then if you buy a house and you expect the house to cost $400,000, but it costs $400,000 and $100, well, that's still a difference of 100 up top. But when you divide by the expected, 400,000, it's not that big of a difference. So now you still have the 100,000 or the 10,000 up top, but now you're dividing by this. So the bottom number standardizes the difference, because this is going to be a very small difference of a chi-squared of 0.025, I believe. It's tiny. So what that would tell you is this difference of $100 is not really that far off from what you would expect, but this difference of $100 is a huge difference. I think we all know that. If you go to buy a candy bar and it costs $101, you're like, well, I thought this was going to cost $1. Or you go to buy a house and you're like, I thought this house would cost $400,000, but it costs $400,000 and $100. And you're like, well, that's not that big of a difference, because you're standardizing by what you expect. It's not just the difference. And the reason we squared, once again, is so all differences are positive. So apparently I deleted out the values in the table that I needed. I did that one time, others. Okay, so let's bring back those values. Let's get the totals here with sum of this. There's the sum of this, the sum of this, the sum of this. And we now need the sum of the grand total of the table. There's the sum of the grand total. And now let's get the... Actually, you know what's funny? Since we did this, we can actually take and do the sum of these. Now, we're going to run into a problem, maybe. One way to check the smallest cell count is to do the smallest row total times the smallest column total. So the expected cell counts here are row total times column total over grand total, which is row total, that's column total, doesn't matter which way you do them in, times row total over grand total. And we actually have a violation of the expected cell count. You must have expected cell counts greater than 5. And we also did this totally wrong. Let me slow down. What we need to do is, if we have this, we need to do equals row total times column total over grand total. And I will say this, hopefully no one said in the chat I'm going too quickly, but check out the earlier questions. If you've just jumped to this question, we went a little slower, and we're going to make sure this formula is right. Now we're going to lock this cell, and then we're going to lock it on 5 so it doesn't go lower, and we're going to lock it on E, and then we are going to hopefully see that 2 again right there. There it is. And so we do have cells that are less than 5, so that creates a problem for the chi-square test of independence. Now we go here and we do observed minus expected squared over expected. So equals the observed, let's put it in parentheses, observed minus expected quantity squared over expected, and that's the value. So here's all the cell chi-squareds right there. And now what do we need to do? Pearson chi-squared test statistic. So the Pearson chi-squared, and then we need our degrees of freedom, and then we need our p-value. So the Pearson chi-squared test statistic is equal to the sum of all the cell chi-squareds. The degrees of freedom here is 4, because you can delete one row and delete one column, and that gets you exactly 4 cells in the middle. What's that? Ooh, I got a new pen right here. Oh, I have to try that. So there are 4 degrees of freedom, and then from here we can do a chi-squared right-tailed test, chi-squared distribution right-tailed test. Nope. Chi-squared distribution right-tailed test, and we put in the chi-squared value and the degrees of freedom. This is going to be quite a large p-value, like 0.7 or so, 0.741. Ooh, got kind of close. And it's going to look something like this, and we're going to be over here. There we go. Space pen. Okay. So let's see if I was right on my drawing of it. So we'd put in, there are, wait. How many degrees of freedom? 4. Nope. I know. I already pulled up the applet, right? I thought it was 2 degrees of freedom. Just so you can see what I thought. I don't know why I thought 2 degrees of freedom, but I literally thought it had 2 degrees of freedom. I even drew my 2 wrong. I guess at 3 it gets the bump. I was thinking the chi-squared of 3. 4 is going to move the bump over more to the right. It starts to get the bump around there. So 4 degrees. How do I lock the values? I'll show that again here, Stephen. This is what it's going to look like. Something like that. And so 4, and then chi-squared at 2.13. There we go. So my drawing right there, and the actual drawing right there of the p-value. So we're very similar-esque. Don't expect you to be able to draw it out, but because the chi-squared, the shape of it dramatically changes from a right-skewed distribution to more of a normal. To lock the cells at a $sign before it. I'll lock the cells at a $sign, and that'll lock the position of the cell. You can also write each one individually. It just takes more time. Row total times column total over grand total. And when you're checking your work, make sure that each cell has the proper things. So make sure you don't have to lock it for the next step, but make sure you lock these, or you just write each one by doing, like, if I don't lock it, like I can do this one right here by saying this has to equal row total times column total divided by grand total. So it can be done without locking them. Does that make sense? And then these don't have to be locked down here. Okay. Well, that's got all the work. Whoops. What did I do? I saved it. Good. You're welcome, Stephen. Good work. Okay. Where'd the question go? And the null hypothesis is that they're independent. The alternative is that they're not independent. We can enter in all of our expected cell counts right here. Boop, boop, boop. I might be able to copy paste. Yeah, I can copy paste. Wait. I literally copy pasted the wrong one in there. Amazing. Which is just like copy my work from Excel. That'd be awesome. Ah! I'm going to misclick somewhere. I know. It just like, cool if they just made like, solve this in Excel and we will check it for you. This is just the busy work portion. It's like I've already solved everything. I already did everything. And the chi-squared test statistic. How many? 2 decimal places. There we go. 2 decimal places. many degrees of freedom? 4 degrees of freedom. P-value of 3 decimal places. And what should we conclude? What do we conclude? I what the null, and I have what for my alternative. What do you do to the null right here? What do you do? What do you do? Your p-value is super duper duper high. Then they won't give you an alpha, but assume 0.05 unless, oh, there's the alpha, 0.05. So we what? Since my p-value is super duper high, I definitely do not reject the null, and I do not have evidence for my alternative that they are not independent. So the alternative was that they're not independent. We don't have evidence for that. Did we do it? We did it. That's 100 on the quiz right there. So I think we've done, might head off and relax for a moment here. But good work, everybody. Is everyone doing great? W Reptar and everyone here. I like Reptar Stat 201. It really makes me smile right there. But I think we're good. I think we've done it. I'm going to head off. Instructors meeting. Mark your calendars. When's this? On the 5th. Oh, got a meeting. You're welcome, John. Thank you, everyone, for being here. Until later. Bye for now. Bye.